job. Please welcome Dee Dee Lavender.
Hi, everybody. Is the microphone on? It feels like it might be. There's a slight vibration. Well, thank you so much for coming to a talk about encryption at 4 o'clock in the afternoon. I see lots of people with coffee cups, which I recommended. My name is Dee Dee Lavender, and I am a back-end engineer working in the payment space at a startup in North Carolina called Spreedly. I'm also a director with Women Who Code in Raleigh-Durham, North Carolina. And I am so glad to be here. I love Connect. I hope you all have had a great day. Encryption is a huge topic. We're going to tackle a chunk of it today, acknowledging that we may represent a wide range of previous experience or understanding of the topic. We'll cover basics and vocabulary as we go. In addition to explaining the different types of encryption and how they work, we'll look at a few examples of how it is used in our lives and why it's important. And I'm hoping we'll have time for the last slide, which just whets your appetite about the future of encryption. So to start, how many of you have ever solved a cryptoquote? Has anybody ever done one of these? I love these so much. I'm going to date myself now, but my sister and I used to find these in the newspaper every day. She would copy them out twice, and then we would race to see who could solve it first. She usually won. But anyway, let's go ahead and define cryptography. Cryptography has very straightforward origins in the Greek language. Kryptos means hidden, graphene meaning to write. Some definitions of cryptography include secret writing, the art of writing or solving codes. More specifically, it's referred to as a field that includes encryption and decryption, which brings us to our topic today, encryption. Most simply, it's a process of converting information or data into a code with the intention of preventing unauthorized access. Early encryption techniques were not as complicated as they are today. Around 600 BC, the ancient Spartans used a device called Ascii, or Skytail, however you want to say it, to send secret messages during battle. So this consisted of a leather strap wrapped around a wooden rod. When the leather strap was unwrapped, the letters were meaningless. They only made sense if the recipient had the correctly sized rod. That's pretty cool, right? Then 500 years later, Julius Caesar invented a substitution method of encryption that shifts the characters of the alphabet. If it were shifted by 3 places, then A would become D, B would become E, and so on. Has anyone heard of the Caesar cipher before? Well, let's define the word cipher. This is one of those fun ones. It could be a noun or a verb. It has multiple definitions and usages. In its simplest sense, it is the method or the algorithm that performs the encryption or the decryption. When using a cipher, the original information is known as the plain text, and the encrypted form as ciphertext. The ciphertext message contains all the information from the plain text message, but not in a format that's readable by human or computer without that proper mechanism to decrypt it. That mechanism is commonly referred to as a key. So in the example of the Ascii, you could say that the cipher was the process of wrapping that leather strip around the rod, and the key was the size of the rod. Similarly, for the Caesar cipher, we could say the cipher was shifting the letters of the alphabet, and the key would be the direction and number of places that they were shifted. Encryption methods obviously have become more sophisticated with time. The idea to use an agreed-upon keyword for encrypting and decrypting emerged. The Playfair Cipher was invented. It encrypted pairs of letters instead of single ones, and therefore was harder to crack. There are many examples of encryption schemes. Does anyone know what this is a picture of?
Is that like World War II?
Yeah, exactly. The Enigma machine. It was invented in 1918, and every time a key was pressed, 3 internal rotors each took in a letter and output a different letter. The original letter passed through all 3 rotors, bounced off a reflector at the end electronically, and was passed back through all 3 rotors in the other direction. There could be a whole talk about just this machine, but we have to keep moving. Now, in 1945, Claude Shannon, a mathematician and electrical engineer, authored a paper called A Mathematical Theory of Cryptography. It was the precursor to another paper published a few years later called A Mathematical Theory of Communication, and that earned him the title, the father of information theory. At this point in history, cryptography and Shannon's work virtually disappear into secret government communications organizations, such as the National Security Agency. Until the 1970s, of course, when things began to get interesting. By now, computers had been around for a bit. Passwords were a thing. There were even a few personal computers out there. Hang on. I think we need to talk about hashing before we get too much further. So these terms are sometimes used interchangeably, but incorrectly so. A hash is not meant to be reversed. Let's take a closer look. Now, this is another one of those words. I'm sorry, my formatting is off. That's supposed to be big and in the middle. This is another one of those words that can be a noun or a verb or an adjective. As an adjective, oh, you know what it is? It's that. This is what I want you to see. Sorry. When it's used as an adjective, like in this diagram, it describes an algorithm that's used to create a fixed length output representing your original data. Which hash are you using? As a verb, hashing describes the transformation of the data into this representative string or number. Let me hash it first. As a noun, hash is used to represent the actual output of the hash function. Here's the hash we need. So in this diagram, you can see various inputs all going through the same algorithm and ending up with an output that is the same length, fixed length. Regardless of the size of the input, and in truth, it could be a single character or an entire novel, it would still come out with the same fixed length result. And if you change even just a little bit, we've changed one word here, you have a completely different outcome. So this is hashing. It's very fast to compute hash values for any size or kind of data. And it should be impossible to regenerate a message from its hash value. In other words, you should not be able to go backwards from that hash output to get that original input. Theoretically, there should be no hash collisions. In other words, each message or each data input should have its own unique hash when put through the hashing algorithm. Again, if an input is changed even slightly, even if you flip one bit, it should significantly change the outcome. So hashing originated from a need to compress data, but it was quickly recognized as a way to create unique identifiers and to ensure integrity. If something about the data changed, you would know because the hash would change. So common hashing algorithms are publicly available tools, and secure hash algorithm, otherwise known as SHA, has a whole family of algorithms out there. For instance, when you make a commit, Git uses an algorithm called SHA-1 to produce a hash of the contents of your commit, and then allows you to reference that commit by the first 8 digits of the hash. Has anyone experienced this? Okay. So hashes are perfect for comparing values when you don't want the raw data stored, like with emails, for example. You know how when you're shopping on the web, and then a few days later, that thing you were considering starts popping up in ads on the other web pages? That is because they're matching the hash of your email address. Kind of creepy, kind of cool. Now, some hashing algorithms can be reverse engineered, and this will continue to be the case as technology becomes more sophisticated every moment. MD5 is probably the most popular hashing algorithm, but typically can be reversed just by tapping the output or the hash into Google. So no longer considered secure. SHA-256 or above is recommended for situations where security is vital, and it produces a 32-byte hash value. Oh gosh, hashing could be a whole nother separate talk as well. Since I mentioned bytes, let's be sure that we're clear about this. Another case of terms that are sometimes mistakenly used interchangeably. While they both transform data into another format, encoding uses publicly available schemes that are intended to be reversed. Decoding only requires knowing which scheme was used to encode. You can think of it like a map or a legend or even a table. Encryption, on the other hand, is meant to protect valuable or sensitive information, and decryption is more complicated. The data is transformed using an algorithm or a series of algorithms plus a secret key, and the intention is that it not be easily reversed. So again, the purpose of encoding is to transform data so that it can be properly and safely consumed by a different type of stream. Morse code, for example, uses dots and dashes of sound or light along with varying length pauses to communicate certain characters over long distances. Another example of encoding that we're all familiar with is Braille, where physical bumps represent letters and symbols. The goal is not to keep information secret, but rather to ensure that it's able to be properly consumed. In the world of computers, encoding refers to how information or data is stored on the computer. We know computers use binary code, comprised of the digits 0 and 1, to store data. To communicate with computers, we have to understand the basics of binary code. That smallest unit of data is called a bit, a 1 or a 0. Groups of 8 bits are called bytes. Here are 4 bytes. This numerical system, binary, maps to all the other number systems. The way you get from binary to our familiar decimal or base 10 number system is super fun and involves powers of 2. Oh, I wish we could talk about that too. Okay, here's a quick look at the number systems lined up. If you didn't get the binary joke earlier, now's your chance to figure it out. So using a number system translation, encoding schemes allow us to communicate or share data with computers. It translates those ones and zeros into language we can understand and process. It's basically a set of mappings between the bytes in the computer and the character set of a language. One of the first encoding standards to become popular is the American Standard Code for Information Interchange, commonly known as Ascii. First published in 1963, Ascii uses 7 bits to encode 128 specified characters. That's 2 to the 7th, 128. 95 of the encode characters are printable. These include the digits 0 to 9, uppercase and lowercase letters A to Z, and punctuation symbols. The original Ascii specification also included 33 non-printing control codes, now mostly obsolete. Now, obviously, 95 characters is not sufficient, and Ascii has been superseded by UTF-8. A whole nother talk in there. Here's an example of UTF-8 encoding. Each byte represents 1 letter or character. So I wanted to go through that about encoding because remember when we said that SHA-256, that hashing algorithm, produced a 32-byte hash value? Well, each byte has 8 bits, and 32 times 8 equals 256. So I wanted to get that context established. So now that we have encoding and hashing covered, let's go back to the 1970s. There were 2 major public advances in encryption in the 1970s. The first publicly sanctioned block cipher, the DES, or Data Encryption Standard, came out. Now, a block cipher is a method of encrypting text to produce ciphertext in which a cryptographic key and algorithm are applied to a block of data, for example, 64 contiguous bits, at once as a group rather than to 1 bit at a time. Now, this is a big leap from the 1920s and the Enigma machine. I wish we had time to go into the math and the exact process of this cipher, but we'll never finish if we start that. The second major development came in the form of a paper that would prove over time to fundamentally change the way crypto systems work. I love the spirit of this first paragraph, and I'm going to read it to you out loud. We stand today on the brink of a revolution in cryptography. The development of cheap digital hardware, this is in the 70s, has freed it from the design limitations of mechanical computing and brought the cost of high-grade cryptographic devices down to where they can be used in such commercial applications as remote cash dispensers and computer terminals. In turn, such applications create a need for new types of cryptographic systems, which minimize the necessity of secure key distribution channels and supply the equivalent of a written signature. At the same time, theoretical developments in information theory and computer science show promise of providing provably secure crypto systems, changing this ancient art into a science. Essentially, they developed a method for two parties that have no prior knowledge of each other to jointly establish a shared secret over an insecure channel. This is like, I have goosebumps. It's amazing. It's called the Diffie-Hellman or DH exchange after the authors of the paper. Now, traditionally, secure encrypted communication between two parties required that they first exchange keys by some secure physical channel. Imagine the limitations of paper key lists being transported by a trusted courier. I love this visual of how the DH key exchange works. You agree on a common color to start with. Only you know your secret color, which you mix with that starting color. You then share the mixed color with each other, re-add your secret color, and now you have the same common secret color. Someone might know your starting color if you communicated that over an insecure channel, but it would be nearly impossible to figure out the common secret color without knowing each individual secret color. Okay, I'm saying colors, but you know this is really about math. Everything is about math. Okay, you can debate me later about that. So far, when we've mentioned keys, we have talked in the singular, one key. Both DES and the DH key exchange are based on a singular key. And there are two types of encryption that are in widespread use today. Symmetric encryption, which means one shared key, and asymmetric encryption. The name is derived from whether or not the same key is used for encryption and decryption, which is the case with symmetric encryption. We can see why it is therefore critical that a secure method exists to transfer or share that key between sender and recipient. This is why Diffie and Hellman's key distribution scheme was so critical. In fact, it laid the groundwork for the next major development in cryptography, asymmetric encryption. Where symmetric encryption uses one shared key, asymmetric encryption uses a key pair, a public key and a private key. It's also known as public key encryption. The public key may be disseminated widely, but the private key should be known only to the owner. Protect your private keys, people. Effective security simply requires keeping the private key private. The public key can be openly distributed without compromising security at all. So the public and private keys in a key pair are inseparable, and of course each pair is unique. The public key belongs to its corresponding private key and only to that one. So one critical application of asymmetric encryption in our modern world is digital signatures. This is something we've all heard of, right? So a digital signature is sometimes referred to as an electronic fingerprint. It accomplishes two main objectives in providing a layer of validation and security for messages. It verifies the sender, and it ensures the data is untampered with. In addition to authenticating the source and the integrity of the data, it offers non-repudiation when necessary. So let's take a quick look at this diagram. We have the signer, or the sender, with their private key and the data they want to send. The data is hashed, which compresses that storage capacity or requirement. Then the hash and the private key are used in a signature algorithm is used with those two things to create the digital signature. That's sent along with the data. Then the verifier, they've gotten the data and the digital signature. They have a verification algorithm using the signer's public key, which matches the sender's private key. Sorry, I'm using sender and signer interchangeably. They can pull out the hash. They're also told what the hashing function was used, which hashing function was used, and they hash the data themselves. So that verification algorithm pulls out the hash from the digital signature. They've hashed the data, and if those two things are equal, we know the message is untampered with. That's cool. It's actually revolutionary. One of the most well-known signature algorithms is RSA. Now, RSA stands for the initial of the three friends who worked out the solution: Ron Rivest, Adi Shamir, and Leonard Alderman. They were all at MIT together, and they were trying to pick up where Diffie and Hellman had left off. D&H, pardon the nicknames, had introduced the idea of asymmetric public-private key pairs, but they didn't formulate the necessary one-way function to produce the key pair. They just said, we think this is possible because of our paint thing. In mathematical terms, a one-way function is known as a trapdoor function, where it's easy to compute but hard to inverse or reverse. So a simple example is, if I ask you, 6,895,601 is the product of two prime numbers. Tell me what those numbers are. That's really hard. That's like really super hard to answer. But conversely, if I said to you, hey, here are two really big prime numbers, what's their product? That would be really easy. You just multiply them and say, here's the answer. So this is an example of a trapdoor function where it's easy one way but hard the other way. So RSA generates two large co-prime numbers, 1,024 bits each, that are not the same. And then they're further put through a series of mathematical operations to generate private and public keys. So RSA is used in digital signatures. It's one of many signature algorithms in current use. This asymmetric encryption also plays a big role in public key infrastructure. Now, this is a fairly simplified diagram of public key infrastructure. What I'm hoping you'll see here is the application of technology we've discussed so far, namely the use of public-private key pairs and digital signatures to achieve the underlying security service. The purpose of a public key infrastructure is to manage keys and certificates. And by managing keys and certificates through a PKI, an organization establishes and maintains a trustworthy network environment. Before the talk, Ruth and I were talking about encryption and how if it's done right with a public key infrastructure, then most people don't even really realize the level of encryption that they're dealing with on a daily basis because it's running so smoothly. Right? So this is an example of like what we call that system of protocols and rules running behind the scenes to employ these types of encryption. A PKA enables the use of encryption and digital signature services across a wide variety of applications. So here are some modern day applications of public key or asymmetric encryption. Whenever you interact with any of these things, you're dealing with like modern day encryption at its finest. Secure email, desktop security, web-based security, e-commerce, access control, virtual private networks, digital signatures. I'm just scratching the surface here. Okay, hang on. We have to back up a bit. I was talking about the DH key exchange and how it laid the groundwork for the innovation of asymmetric encryption. But I want to circle back to symmetric encryption and how it's used today, because there have been lots of advances. When we left off talking about DES, does anyone remember what that stands for? Data Encryption Standard. It uses a relatively small key, only 56 bits, and it has been broken in cryptography terms. That's why I'm using this picture. So something could be broken, but still in use. Right? In the world of encryption, broken means something very specific. It means simply that it can be solved faster. Let's see, that it can be solved in faster than brute force time. So brute force time is basically guessing. Even if you use a systemized approach or a systematic approach, you're still basically guessing, and that's what we call brute force. So if a solution has emerged that is faster than the time it would take for a brute force attack, then the algorithm is considered broken. But it doesn't mean that it's easy to solve it. It just means that it's possible. But improvements were made over time, and perhaps you've heard about 3DS or triple DES. That basically just used a key bundle comprised of 3 DES keys, each still 56 bits. That one's also technically broken, but doesn't mean it's not still in use, just not in ultra-secure applications. I use my glasses until they're unusable, not just broken. Okay, so in 1977, in response to those attacks on DES and triple DES, the National Institute of Standards put out a call for submissions for an advanced encryption standard. The algorithms were to be block ciphers. Remember that encrypting blocks at a time, or chunks at a time. And the block size should be supported up to 128 bits. And the key sizes should be 128, 192, and 256 bits. So those were sort of the parameters. We want a new block cipher with these parameters. The process took 5 years. And there were some amazing submissions. The official choice was declared in 2001 and remains the standard today. Now, some of those other submissions are also still in use. The Rheindahl algorithm was the winner, and it's now the basis of the AES, or Advanced Encryption Standard. The algorithm was designed by 2 Belgian cryptologists, Vincent Riemann and Joan Damon, whose surnames are reflected in the cipher's name. Rheindahl is a substitution linear transformation cipher. That's like a lot of words, but it uses triple discrete invertible uniform layers, or transformations. And overall, the structure of Rheindahl displays a high degree of modular design, which is part of why it was chosen, so modifications could be made to counter future attacks easily, and much simpler than with past algorithms. So, although this Rheindahl algorithm underpins the AES and is approved in the United States for high-level government documents, etc., there are many other symmetric algorithms in use. So some of the things in our daily lives where we see symmetric encryption include payment applications, secure file transfer protocols like FTPS, HTTPS, SFTP, etc., the encryption of files, the encryption of file systems, tools for archiving and compressing data. So one advantage that symmetric encryption has over asymmetric encryption is its speed. Asymmetric encryption has added layers of security with those public and private keys, but the trade-off is processing speed. So many modern-day encryption protocols combine these two types of encryption. One example of this combination approach is TLS, or the Transport Layer Security. So TLS supersedes SSL protocol. Remember that? Secure Socket Layer. So TLS is a cryptographic protocol that provides end-to-end communications security over networks and is widely used for internet communications and online transactions. The IETF, or Internet Engineering Task Force, has set it as a standard intended to prevent eavesdropping, tampering, and message forgery. Common applications that employ TLS include web browsers, instant messaging, email, voice over IP, the list goes on. Has anyone been impacted by recent upgrade or upgrade requirements to TLS 1.2 or 1.3? Super fun. So when we talk about encrypting data, there is sometimes a distinction used between data in motion versus data at rest. And this is worth thinking about if you are responsible for helping to ensure or provide encryption. So for protecting data in motion or in transit, businesses often choose to encrypt sensitive data prior to moving the data, and then to use encrypted connections like HTTPS or TLS to protect the contents of the data in transit. And then for protecting data at rest, enterprises can simply encrypt sensitive files prior to storing them and or choose to encrypt the storage mechanism itself. Okay. Did I go too fast? Okay, well, if I did, I'm sorry, but I'm happy to talk about things afterwards because this is our last slide. And this one is super exciting. So this is just to whet your appetite about the future of encryption. Has anyone heard of quantum cryptography? So exciting. It's like mind-bending and awesome. Soon, quantum computers will render some of our strongest encryption protocols useless, cracking asymmetric encryption in seconds, thanks to their ability to quickly work out those long prime numbers used to generate them. So without getting too deep into quantum physics, quantum key distribution all hinges on the fact that measuring the state of a photon actually changes that state. What? So don't worry, if you have lots of time if you want to get in on quantum cryptography solutions. The most powerful quantum computers in existence can only handle about 72 qubits or quantum bits, meaning that they can only deal with strings 72 bits long. That's far shorter than most cryptographic keys. So like I said, there's time, I don't know how much, that if you want to be a part of those solutions for handling cryptographic quantum cryptography, there's time for you to get in on it. Thank you so much for listening. I'm happy to chat afterwards if you have any thoughts or questions. And happy Connect. Okay, good. A few minutes early, but not too bad.
One is I made up my own pun, which I think you're going to enjoy.
Okay.
What does a security programmer do to a potato? Well, people usually say hash it, and then I say, that's bad practice to salt, then hash.
Very nice.
But I was like,
That's really I thought about getting into like salting and peppers and all that, but that's really more hashing specific. But I do think that the intersection of hashing and encryption and all that is really super interesting. Oh, thank you so much. Chocolate. Oh, thank you so much. I'm glad you could come. Oh, fun. That's awesome. Well, check out CryptoQuotes. What? Check out CryptoQuotes. They're really cool. They're super fun. Yeah. Oh, yeah. Old ones.
I wonder if I still would be.
Yeah, because you have to look for patterns and with commas and across